So you may have clicked on the thumbnail and you're wondering, why is he showing a One Piece manga panel? If you stick around for this entire video, I'll tell you. Coulomb's law states the force between charges proportionally increases, and as you move those charged particles apart, the force between them decreases exponentially. So Fe, the electrostatic force between any two charges, is equal to K, which is a constant that we'll get into in a second, Q subscript 1, so object 1's charge, and Q2, object 2's charge, divided by r squared, and K is equal to 8.99 times 10 to the power of 9 newtons meter squared per coulomb squared. Now you may be wondering, wait, coulombs? What are coulombs? Well, coulombs are the units of the charge. So if we have like a blue ball here and a red ball here, let's say that the blue ball's charge is 2.0 coulombs and the red charge is negative 2.0 coulombs. These integers, they don't represent directions, they actually represent like the this is a positive charge and this is a negative charge, so these will be attracted to each other. However, with regards to these charges, yes, they're attracting each other. So you would think, you do K multiplied by negative 2 multiplied by 2 over whatever distance they have between them. But for the electrostatic force, we just want the absolute value of the electrostatic force. So whether the charge is negative or positive, we want our electrostatic force to be a positive number. So like, let's say the distance between these two charged particles is like 2 meters. So we do 8.99 to the power of 9 multiplied by negative 2 times 2, and all of that over 2 squared, because that's the distance. Remember, the distance between them is 2 meters, so we put 2 there. The charge of the red ball is negative 2, the charge of the blue ball is 2. Makes the electrostatic force this number, but we want the absolute value of the electrostatic force, so it'll be actually positive 8.99 times 10 to the power of 9. And let's say we were measuring the electrostatic force on the red ball, we'd be saying that it's going right, because the red ball is going to be attracted to the blue ball. So a comb with negative 2.0 microcoulombs of charge is 0.15 meters to the left from a hair with positive 3 microcoulombs of charge. And now we're looking for Fe. So we know that electrostatic force is equal to K Q1 Q2 over r squared. So let's just plug in our values. So first the constant K, 8.99 times 10 to the power of 9. And now for object 1's charge, and if you can notice, it's actually in microcoulombs, so we're just going to convert this to coulombs. Negative 2 times 10 to the power of negative 6, and then get object 3, which is going to be 3 times 10 to the power of negative 6 coulombs, and then divide all of this by the radius squared. And then after all that, just take the absolute value of the answer. So the electrostatic force is 2.4 Newton, and this is negatively charged while this is positively charged. So we know that the attraction for the comb is going to go this way. So the force the hair exerts on the comb will be going the right direction. Now you might have noticed, hey, why did he put it in microcoulombs? Is he just making us do extra work for no reason? No, it's because in most situations the charges will be in the range of 10 to the negative 6, because only like really special cases like a lightning bolt striking down will have a charge of like 1 Coulomb or larger. And just take note that 1.60 times 10 to the power of negative 19 coulombs is equal to the charge of 1 electron. So if something actually has a charge of 1 Coulomb, it has a lot of electrons. And because it's an electron, the charge here is going to be negative. And then for a proton, it'll be 1.60 times 10 to the power of negative 19 coulombs, but it's positive because it's equal to 1 proton. So it's telling us to determine the net force acting on the charge at the far right, so this charge right here. So all you really do is just calculate the Fe for this, and then after you finish that, calculate the Fe for this, and then just add up the vectors. So I'll do electrostatic force, and then I'll like put a red dot beside it so we know it's corresponding to this and this. So it's equal to K value 8.99 E9 times 10 to the power of 9 multiplied by charge 1. So let's put that 1.5 times 10 to the negative 7. And then the other charge, which is this. And because we're going to take the absolute value of Fe anyways, there's no point in like writing out the integers. Just do 3.5 times 10 to the power of negative 4. Because yeah, you could write the negative sign here, but like your answer for Fe is going to be positive anyways, so why do that? Divided by the radius, so just add up these two numbers, so 1.4 plus 1.7. 1.4 plus 1.7, and that gives you 3.1. Can't forget to square it. You'll get a Fe for Q1 and Q3 is equal to 0.05 newtons, and because Q1 is positively charged and Q3 is negatively charged, it's going to be attracted to Q1, which is going in, and that attraction is going left. So we're going to write 0.05 newtons left. So now let's do the calculation for Q2 and Q3, and then black dot just as a reminder that we're doing this and this. So once again, the constant for K, 8.99 times 10 to the power of 9, multiplied by 2.3 times 10 to the power of negative 7, multiplied by 3.5 times 10 to the power of negative 4, divided by r squared, which here is 1.7 squared. So we get that it's like 0.25 newtons, and because these are both negatively charged, this one does not want to go there. It's to go away from there. So this will be right. And then just add the vectors together. This one going right is 0.25, and this one is 0.05. So if we say that left is negative, then we can just do 0.25 plus negative 0.05, and this gives us 0.20 newtons. And because it's the right direction that's overpowering it, we do right, because the right vector is greater. So we are trying to determine the net force on Q2 for this. So step 1, let's just calculate the electrostatic forces individually. So first I'm going to do Fe blue to, remind us we're doing these. And that's going to be the constant of K times the charge of Q2, then the charge of Q1, and then the radius squared, and 19977777778. We know that because this is positive and this is also positive, it is definitely not going up. It wants to get away from it, so it's going to go down. And then let's do the same thing, but for the green ball. Or the green charge, not ball, sorry. So anyways, once again, because these are both positively charged, the red ball does not want to go this direction. it wants to go opposite of it, so this direction. So yeah, anyways, Q2 is being pushed down, and it's also being pushed left, and this creates a triangle. So the force pushing it left, as we measured, was 224750000, and this was 199777778. So now using Pythagorean, we can determine the net force. So, and we get that it's 3.0 times 10 to the power of 9 newtons. So yeah, that's our net force. And for the angle, I'm gonna use tangent, but you can use sine or cosine since you know the hypotenuse. So let's just do tan inverse of that long number divided by the other also pretty long number, and you get that it's 42 degrees west of south. Anyways, so as I was saying earlier at the very beginning of the video, because you made it this far, I guess I will explain why I used this panel in the thumbnail. So the lightning bolts from Luffy's punch is his Conqueror's Haki. But what makes it so Luffy is able to punch Kaido without even touching it? Well, as we know, lightning, as I previously said in the video, has a lot of electrons behind it, because one lightning bolt is 1 Coulomb, and as we can see here is 1, 2, 3, 4. 4 lightning bolts, which is equal to 4 Coulombs. As we know, in 1 electron, there's 1.60 times 10 to the power of negative 19 Coulombs. So to get the amount of electrons that are in this, we just gotta, cancel out the Coulomb. So that means there is 2.5 times 10 to the power of 19 electrons in that attack. And we know that Kaido is incredibly strong, one of the reasons being that he coats himself in Advanced Conqueror's Haki. So if the Advanced Conqueror's Haki, which is negatively charged, clashes with the coating of the Advanced Conqueror's Haki, which is also negatively charged, this will repel each other, allowing Luffy to land a pretty powerful punch on Kaido.